students. In the last class we discussed up to the comparison of the transverse waves and the longitudinal waves, and now today we are going to discuss the terms and definitions used in the wave motions. Two different sinusoidal waves has to be given in this diagram. So in the along the x and y axis, suppose we have the two waves, or these two waves are identical? No. Though the two waves are both sinusoidal, there are many differences between them. Before, we have to define some basic terminologies to distinguish one wave from the another. Okay, so considering a wave produced in a stretched sink. So you know that you are all studied this type of waves in the 9th standard and the 10th standard itself, right? Crest and trough, and then compression and rarefaction. This will be you're getting in the wave formation. So now we are considering a wave that will be produced in the stretching string. You know what is string and how it was stretched. So in the stretched strings we are getting the waves like this, and that upside peaks are called as a crest and the downward is called as a trough. So what happened if we are interested in counting the number of waves created? Let us put a reference level. So here the mean position is the horizontal line. See here, which is mean position means the horizontal line in between it, no, that is the mean position of this. Okay, mean position. And what is the next thing has to be given is the highest point in the shaded portion is called crest. So which has to be the highest portion? That is the crest. And which is a trough means with respect to the reference level, the lowest point on the unshaded portion, that is called trough. So these waves contains a repetition of a section O to B, and hence we define the smallest section without repetition as one wavelength. Okay, so the length OB or the BD in one wavelength, the Greek letter lambda is used to denote one wavelength. So here they are given which has to be a one wavelength. So from O to B, and the one crest has to be there, and also the trough, that is one complete wave. Okay, it will be started from the point of O and end with the B. So end with B. So that is called as an one complete wave. So that is taken as a wavelength of 1 lambda. And see here they are taken the 2 complete cycle. So that is called as an 2 lambda. So 2 complete cycles are there. So that is called as an 2 lambda. Okay, so first one it's 1 lambda and the second one is 2 lambda. So how we are defining it? For the transverse wave, the distance between the true neighboring crest and the trough is known as the wavelength. Okay, distance between the two neighboring crest and the trough is known as what? Wavelength. That is for the transverse waves. And for the longitudinal waves, the distance between, for longitudinal waves means there will not be a crest and trough, there will be a compressions and the rarefactions. So for longitudinal waves, the distance between the two neighboring compressions or rarefactions is known as a wavelength. So therefore the SI unit of the wavelength is nothing but a meter, because wavelength is what? It's a distance. Okay, it's a distance. So what is the unit of the distance? Meter. So same we are taking for the wavelength also, that is for the lambda also. So what is the next step? So some diagrams will be given for the wavelength. So what is a wavelength? You have to understand. For that sake they are given as a full diagrammatic picture. Here see the up to the peak level to peak level is called as an lambda. Here also up to peak level to peak level, this is a lambda. Okay, so it will be very clearly given that lambda. So and then the next diagram is given. So in this spring, this up to the last level to the this level, this will be a lambda. So clearly given this for the transverse wave. For the longitudinal means the lambda will be from stretched to stretched, it's a lambda. From compression to compression, that's a lambda. That is a wavelength of the longitudinal wave. Understood these things? So what is the transverse waves longitudinal, and then the transverse longitudinal waves wavelength and transverse waves wavelength. And next we pass on to the next topic, that is given here as, so all these example problems we'll see later. So the velocity of the waves in the different media. Suppose a hammer is struck on the long rails at a distance, and when a person keeps his ear near the rails at the other end, he or she will hear the two sounds at the different instants. So that the sound is heard through the nails, that is in the solid medium, is faster than the sound we hear the air in the gaseous medium. This implies the velocity of the sound is different in different mediums. So velocity of the sound is different in the different medium. So in this session we shall derive the velocity of the waves in two different cases. One, the velocity of a transverse waves along a stretched string. Other one, the velocity of the longitudinal waves in the elastic medium we are going to discuss. So first of all, what is the velocity of the transverse waves in a stretched string? So let us compute the velocity of the transverse traveling waves on a string when a jerk is given at one end of the rope. What happened? The wave pulses move towards the right end of the velocity v with respect to an observer. Okay, and this will be, we already seen in this. So that will be going to the observer who is at the wrist frame. So considering an elemental segment is in the string, let A and B be the 2 points on the string at the instant of time. So what is, let the DL and DM be the length and mass of the instrumental string respectively. So by the definition, the linear mass density will be given as mu. Okay, the mu is nothing but dm by dl. So dm is equal to mu dl. So elemental string AB has a curvature which looks like an arc of the circle with the center of O, and the radius r and arc subtending an angle theta at the origin O. So the angle theta will be written in terms of a arc length and the radius theta dl by capital R. So centripetal acceleration supplied by the tension in the string is ACP is equal to V square by R. So what is centripetal force? FCP is equal to dm into V square by R. So what is the equation? So comparing this two equation, we are getting dm V square by R is equal to mu V square dl by R. So the tension T acts along the tangent of the elemental segment of the string at A and P. So the arc length is very small, the variation. So the diagrams has to be given, whatever the diagrams we are discussed, that will be given in the form of what? Diagram. Okay, so the elemental segment in the stretched string is zoomed and the pulse seen from an observer who moves with the velocity v. So what is given already? The length is very small, whether the tension force will be ignored. So length itself is very small. So when we are taking the tension force, means that is also very small. So we are ignoring that. It can be resolved that T into horizontal component, that is T as theta by 2, and the vertical T cos theta by 2, and the vertical component is T sin into theta by 2. So horizontal components at A and B are equal in magnitude but opposite in direction. Therefore, they can cancel each other. Since the elemental arc length AB is taken to be very small, the vertical components at AB appears to act vertical towards the center of the arc, and hence they add up. So what is the net radial force? Fr is nothing but the radial force, that is equal to 2t sin theta by 2. So what is the amplitude of the wave? Is very small when compared to the length of the string. So sin theta by 2 is equal to or approximately equal to theta by 2. So what is we are taken? Fr is equal to sin theta by 2. Here sin theta by 2 is nothing but theta by 2. So we have substituted it. 2 get cancelled. It becomes t into theta. So what is the value of theta? dl by r. So substituting that value, we are getting Fr is equal to T dl by r. So by applying the Newton's second law, the elemental string in the radial direction under equilibrium, the radial component of the force is equal to the centripetal force. So hence the equating equation is nothing but T dl r is equal to mu v square dl r. dl get cancelled because both will be same on other opposite sides. So it will be getting cancelled. So what is T is equal to mu v square. So if you are finding the v, means the mu will be going on that side. So it will become v square is equal to T by mu, and if you are taking the square root, it will become v is equal to square root of T by u. Okay, so observation, the velocity of the string is what? Directly proportional to the square root of the tension force and inversely proportional to the square root of the what? A tension force is T. So V is directly proportional to T is in the numerator, no? So that's why we are telling that V is directly proportional to the square root of the tension force, but where is mu? It is in the denominator side. So that's why we are telling that inversely proportional to the square root of the linear mass density. Independent of a shape of the wave. So it's also independent of the shape of the waves. So related with this, one more problem is given. We will see the problems later. So next we pass on to the velocity of the longitudinal wave is an elastic medium. So for this medium, we assume the air. We assume the air and having a fixed mass containing a long tube cylinder whose cross section is A and maintained under the pressure of P. So one can generate longitudinal waves in the fluid either by displacing the fluid using a piston or by keeping the vibrating tuning fork at one end of the tube. So what happened? We are assuming that direction of propagation of waves is coincide with what? Axis of the cylinder. So what is the let rho, that is the density of the fluid which is initially at rest, means T is equal to 0. So the piston has left end of the tube is set in motion towards the right with the speed of u. So u be the velocity of the piston and v be the velocity of the elastic wave. So in time interval t, the distance moved by the piston, that is del d is equal to u into del t. So now the distance moved by the elastic disturbances is del x is equal to del x is equal to v del t. So let del m be the mass of the air that has attained a velocity in the time of del t. So that is equal to del m is equal to rho a del x. That is written as rho a v del t. So the momentum impaired due to the motion of the piston with the velocity of u. So in place of again we are going to write the equation in terms of what? Momentum. So that's why we are taking the velocity also u. So momentum means it is denoted by what? Momentum is equal to what? Momentum P is equal to m into the velocity, right? So here we are taking the mu. So what is the m value already? Rho a del x, that is v del t into u. So that is del p is nothing but the momentum. So for momentum we are writing. But the change in momentum is impulse. So net impulse is I is equal to del p a del t. Okay, and that is rho a v del t by u. So del p is nothing but rho v u. When the sound waves passes through the air, the small volume element of the wave undergoes a regular compression and rarefaction. The change in the pressure can be written as where v is that is del p is equal to k into del k by del v. So where v is the original volume and k is known as the bulk modulus of the elastic medium. So when v is equal to a del x, that is equal to a v del t. Then del v is nothing but a del d. So that is equal to a u del t. Therefore del p is equal to k into a u del t by a v del t. That is all the thing will get cancelled and only k into u by v. And comparing the equation, you will get rho vu is equal to k into u by v, or otherwise we are taking v on one side means v square will come and u get cancelled, and that p will be coming on this, rho will be coming on this side. It will becomes what? V square is equal to k by rho. So q is equal to root of k by rho. In general, the velocity of the longitudinal waves in elastic medium, that is v is equal to root of e by rho, where e is a modulus of the elastic medium. So in the special cases, for a solid one dimensional rod is there means y is a Young's modulus of the material rod and rho is the density of the rod. The ID rod will have only the Young's modulus. Three-dimensional rod is the speed of the longitudinal wave is in a solid is where n, the speed is given as root of k plus 4 by 3 eta by rho, where eta is a modulus of rigidity, k is the bulk modulus and rho is the density of the rod. Okay, so that is given here. And the next cases for the liquid. So what happened when k or v is a bulk modulus, rho is the density of the rod. So calculate the bulk modulus. So what is given? V is equal to root of y by p. We are substituted and finding the values. 5 into 10 to the power of 3 meter per second. Okay. Next we will pass on to the next topic, that is propagation of sound waves. We know that the sound waves are longitudinal waves, but when they are propagate, compression and rarefactions are formed. In the following section, we compute the speed of sound in air by the Newton's method and also discuss the Laplace correction and the factors affecting the sound in air. First of all, the Newton's formula of speed of sound waves in air is nothing but Isaac Newton assumed that when the sound propagates in air, the formation of the compression and the rarefaction takes place in a very slow manner, so that the process is an isothermal in nature. That is, the heat produced during compression and the heat lost occur when over a period of the time such the temperature of the medium remains constant. Therefore, by treating the air molecules to form an ideal gas, the change in pressure and volume obey the Boyle's law mathematically. So PV is equal to constant, differentiating that we get P dV plus V dP is equal to 0. So that is P is equal to minus V into dP by dV, that is equal to K1. K1 is a isothermal bulk modulus of air. Now substituting the equation in the equation of 11.16, the speed of the sound in air is VR is equal to root of K1 by rho equal to root of P by rho. So that is the thing given. Since P is the pressure of the air whose value is at NTP, so we know that NTP, normal temperature and pressure. So 76 centimeter of mercury, we have P is equal to H rho G. Okay. So what is P? What is H value? 0.76, and what is the value of rho? 13.6 into 10 to the power of 3 into G value, acceleration due to gravity, is always 9.8. So multiplying all these things, you are getting the answer as 1.293 kg per meter cube. Okay, so then the speed of the sound in air at normal, the temperature and the pressure is Vt is equal to root of the values they are substituted. So that will becomes 279.80 meter per second value. So that is 280 meter per second. It's a theoretical value. But the speed of the sound in air at 0 degree Celsius is supplementally 332 meter per second. So which is closed up to the 16% more the theoretical value. Okay, so that is a percentage error. This error is a small, not a small one. Understood?